to define what is a feature. A feature is a quantifiable or measurable characteristics of a phenomena being observed. So wherever we have an event, in this event, if we have some quantifiable characteristics, then we can say that is feature. For an example, here already we have seen this kind of a data set we discussed earlier. So here, if we talk about the feature, so these are the feature, BP, blood pressure, heartbeat, weight, these are the features, and this is the class. And again, this problem is also discussed. Iris problem. In iris problem, these are called feature. Sepal length, sepal width, petal length, petal width, these are called actually features. So today we are today we are going to discuss about the feature engineering, what we can do on the feature so that the accuracy of the system somehow can be optimized. That's the objective. So initially in machine learning, there are different kind of categories, different kind of basis by which a feature can be categorized. But especially in machine learning, if you see, the features are categorized into two categories. There are different categories, but especially in most of the cases, we can see that there are two kind of features, and these are discrete feature and the continuous feature. What's a discrete feature? It can take only certain values, but it can be numerical or it can be categorical. So see here, in case of this iris data set, say for an example, we had values. So these values are replaced by some categories, say big, big, big. And here we have a medium, medium, small. Here medium, small, medium. Like that, if we represent the data or the attributes in that way, then we can say these are the discrete features. And similarly, you try to understand discrete feature doesn't mean only the categorical feature. It can be also numerical feature. The same thing. Say for an example, the big is represented by 3. Then we can represent it 3, 3, 3 like that. Here 2, 2, 1 because medium is represented by 2. It is up to you. For the example only, for illustration purpose here, we have taken medium as 2, 2, 2 and small is 1. Like that, we can represent the features. Whenever the features are represented like that, then we can say these are the discrete features. Because in machine learning, we have certain kind of algorithms where we're going to use only the discrete feature to train the model. And now here we have the continuous feature. So if the feature are like that, say here BP is represented by 120, 125, 130, the heartbeat is represented by 70, 65, 59, weight is like that. If such kind of feature is there, then we can say as a continuous feature. What is the characteristics? The characteristics of feature is that it can take any value within a range. For an example, so we have weight here. So weight 50 to 100, say. So here we can take it 50.1, 50.02, 50.5. So it can take any value within the range. So if we have such kind of feature, then we can say that is continuous feature. So here we have seen two kinds of features, especially in machine learning. We can say discrete or continuous. But there are different kind of features here. We have the category, but I'm not going to talk about here these categories here. So now, if we analyze the feature engineering or the feature analysis, then the feature has to be analyzed in 3 parameters. And these parameters are feature transformation, feature selection, then feature weighting. So in this presentation, we're going to talk about the feature transformation and feature selection. We're not going to talk about feature weighting. But again, telling you the feature weighting is not always used. We can have a special kind of machine learning paradigm where feature weighting is required. So here in this presentation, we are going to talk about only feature transformation and feature selection. Again, in feature transformation, this can be analyzed in 2 dimensions. These are the feature construction and feature extraction. So first of all, what is feature construction? See the definition here. It generates a new set of more powerful feature from a given set of input feature. Say there are n features, and after feature construction, say m new features are added there. So if it is, then total number of features would be n plus m. So you try to understand, we can have a features, and then from the feature set, we can generate some new features. So if the number of new feature is m, and the earlier feature is n, then total number of features can be n plus m. So see here, we have an example here. So here, this example is represented by this table. We have ln, area length, and we have area breadth. And finally, we found here the price. Price is this, price is this, price is this. If area length, area breadth are like that. Now from area length and area breadth, we can create one new feature, and that is area or a area. So length into breadth, we can see here the area. This into this into this into this. What is the meaning here? Initially, we had two features, this and this. After doing feature construction, we have created one new feature, that is area. So this feature is added here. So now the total number of feature becomes how many? 3. Using 3 feature, we can do the prediction here. Now we have questions that why we do actually this feature construction. So generally, the feature constructions are done for this reason. For this reason, you can see here the reasons. Reasons are when features have categorical value and machine learning needs numerical value inputs. Sometimes we can have a machine learning algorithms where the algorithms need to have numerical values. In that, need to have a numerical values. That in that case, if we have a categorical values, those values have to be converted into numerical values. For an example, so neural network especially take the numerical values. So if we have a problem with say categorical values, and if you want to train, then those categorical values has to be converted into numerical values. So whenever a kind of conversion is done, that is called feature construction. Similarly, when features having continuous value and need to be converted to discrete or ordinary value, then again we have to do feature construction. So in some machine learning algorithms, for an example, a decision tree, even if we are having say continuous values are discretized, and then only the decision tree can be trained. So in some situation, machine learning need to have as discrete values. So in such a situation, if you have some continuous values, then those values have to be converted into discrete values. And then when text specific feature construction need to be done, means we can have a textual data or text processing or text classification. In that cases, actually this feature construction have to be done. We're going to see with an example later. I'll show you an example how if you have a textual data, if you want to do say text processing, then what we need to, because the first step of that is feature construction. We're coming to discuss on that. And sometimes whenever we construct the features, if we expect new features, if we add the new features to the older features, so the number of features is increased. In such a scenario, sometimes it improves the performance of the system. So that's why I have written sometimes improves system performance if we do feature construction. And here we have an example of the feature construction. You can see here, so initially we have a this set, and our objective is to train here. Age is 18, city of origins A, and at the same time we're having different kind of cities here. Here we have a city A, city B, city C. We're having 3 cities, but we have represented all those cities in a single column. And then we have a parent athlete, yes, no kind of thing. Based on that, we are predicting here whether there is chance of win or not. So here we can say these are the inputs or the parameters. These are the inputs, or you can say the attributes 1, 2, 3. Based on these 3 attributes, we're going to predict the output here. So like that, we have a data set. Now we try to understand if you want to use in this machine learning algorithms where the algorithm uses the numerical values. In that case, actually we need to convert it to numerical values, only then we can train the machine learning algorithm can be trained in the data set. So one of the example by which it can be done here, see, so we have about 18 is here, 20 here, 23 like that. Age, in the age there is no change. But try to understand here in the city we're having 3 cities. So now for 3 cities we're having single column, but we're having 3 different options here. So now for 3 different options we can create 3 different columns. So city 1, city B, city A, city B, city C. So in the first case we're having city A. That's why for city A column we have given 1 for this particular observation, and city B the value is 0, city C the value is 0. And here in this case on the parent athlete, because it is yes and no, and it can be represented by only 2 values, 0 and 1. That's why it is represented by, if it is yes, then it is represented by 1. If it is no, it is represented by 0. And chance of win again, it is yes, no. So we're having 2 options. So here we made it by 1 and 0. So like that, whenever we have this kind of database, and if we want to train it where the machine learning algorithm needs some numerical values, then we have to construct the data. So it's a kind of data construction. Try to understand. It's a kind of data construction, means we are now converting categorical values into numerical values. Similarly, we can have this kind of situation where we have this kind of options, right? These are categorical values, but say these values need to have a discrete in terms of numerical values. So then again, we can convert. Similarly here, B can be 2, C can be 3, A can be 1. It is up to you, right? So whenever we do this kind of thing, this kind of scenario is called a case of feature construction. Similarly, this can be one of the case. This can be one of the case, right? So we're not going to discuss about this one. This can be one of the case. So now, so case here, I'm just touching here. So here we have a prices, and prices are in continuous, right? Here the objective is to convert the continuous values into categorical values. Simply we can do, right? So we can give some threshold. Say according to the threshold, say 23 lakh can be represented by medium. So here we have a medium, right? And this one is low, this is low, this is medium, this is low, this is high kind of thing, right? Now, if we have this one, if you want to make it again, say discrete, but in the numerical form, then again, it can be converted like that. So whenever we do such kind of things, actually, that is called feature construction. We can have a different situation for the feature construction here, right? Somebody was interested first day. Now say we want to make once a recommendation system. And the recommendation system here, we're going to make for the movie review. So initially we have to train a model. So once the model is trained, so whenever some reviews would be given there, then automatically the model can say whether the movie is good or bad. So initially the model has to be trained, right? That's our objective, being say technical person. So say we are having this kind of reviews for a particular movie. There's many reviews of movies are there, right? Many reviews are there. And now, so just I have taken an example here. The first review is like that the movie is good, thrilling, attractive. It is up to my expectation. And some kind of rating is there. Or some positive symbol is there, or some positive, negative.
Just a second, sir.
Done, now done.
Okay.
Sort it out. So now we can have this kind of situation, right? Similarly, we can have another review. Here we can have certain kind of rating or something kind of thing, but some kind of thing. And by looking at here, we can understand this is good or bad. When we design that, try to understand during the design of the model. So say these are the good reviews by some mechanism. And we have another review here. That is what? That is bad. It's a review. The movie was loser, lonely, it was bored, it was thrilling. Say it is a negative. Some kind of rating is there, and based on the rating, it is negative now. Now, if we have this kind of thing, what do we need to do? Because whenever we are having some social data, data which are available over the web, lot of noises would be there. So somehow we have to do the pre-processing. So one of the thing in the text processing, that is called stopwatch removal. So whenever we have this kind of words, the, is, those kinds of words are not considered for processing. So initially we have to construct the feature, right? So we can take the words or the terms. So we are looking here that we have a movie, good, thrilling, attractive, expectation. Again here, movie, good, attractive, like that. Here we have something. So now we can see all the reviews, and from all the reviews we have observed that there are how many terms? Different terms. 1, 2, 3, 4, 5, 6, 7, 8 only, right? This is an example. There can be hundreds and thousands of different terms, but here we have taken just 8 different terms are there. So now we have to construct the feature and try to understand when you work with the textual data, then the feature construction or the feature representation or the text representation can be done in 2 ways. One model is called VSM model, another one is called GBM model. So this is vector space model. In case of vector space model, the whole table is represented like that. It's a tabular form. In a tabular form, the whole keywords are represented. Now what we need to do, We need to keep all the words. These words are called features. Now we are constructing the features. So if we want to represent the good now we have to see against this thrilling, whether thrilling is available in the first review or not. Yes, so we kept here 1. This is one of the strategy. You try to understand, you can use a different kind of strategy. You can use, say, word frequency, TF, IDF, any measure you can use, right? So here this is 1. So movie is there or not? Yeah, movie is there. Where? Yeah. So 1. Good is there? Yes, good is there. So attractive is there? Yes. Loser is there? No, 0. Lonely is there? No, 0. Expectation is there? Yes. That's why 1. Bored is there in the first one? No, bored is not there. So that's why this is 0. But try to understand here the classification is what? This is positive. And we have considered in this data set the positive class is representing by 1. So that's why we have written here 1. Similarly, we can do for the second review, and here we have given the third review. In the third review, you can see how many are there: movie, good, attractive, and expectation, and still it is good, right? So against thrilling, it's a 0. Movie, it is 1. Good against a 1. Attractive, 1. Loser, 0. Lonely, 0. Expectation, 1. And now the label is 1. Similarly, for the negative one, here we can give the words which are available in the reviews. So here you can see the fifth number. Movie is there, right? Movie is there, yes, 1. So loser is there, right? So loser 1. Lonely is there, right? For lonely, this is again 1. Thrilling is there, yes, for thrilling it is 1, right? But the class level is what? The class level is negative. That's why it is given as 0. So in that way, actually, initially, whenever we are having the different kind of reviews, those reviews have to be represented. And if we represent like that, that is called feature construction. So we can have thousands and millions of features here. So out of 1,000 features, later on, we may consider all features are not equal, so that we can find or we can make keyword extraction. Some of the words or some of the terms can be treated as keyword. And that is, in data science, is called feature extraction. That is, wait a bit, please.
Wait for 2 minutes, participants. Now, sir is talking about the movie recommendation system. So, if you want to build a movie recommendation system, then how to build your features. You may take data from Twitter or any social media platform, but the data is not ready for your building any model by any machine learning technique. So, before that, what are the features that are necessary and how to construct your features. So, you can see in this slide, sir is showing about the different category of movies. So 1 and 0 means it's what type of movie sir is talking about. So it is a multi-class classification problem. Okay. So in this multi-class classification problem, how to build a, there are so many machine learning techniques that can be applicable for a movie recommendation system. That is the discussion or the example of today's class. So in this slide, you can see that for your feature constructions, there are two popular models are there. One is called vector space model and graph-based model is there. So for feature selection, these two techniques you can use it. So for each technique, you can check the accuracy by applying the machine learning model. So which one works better for your data set, you can find it out always. So you can see multiple classes are there for a movie. So these are called the class labels. You need to understand, and it is a binary classification problem. So in binary classification, we take only two values, 1 and 0. After this feature construction will be over, then we'll go for how to build the model. So machine learning models will be discussed, where how to build your model when your data is ready or when your features are ready. Then by taking the features, we will construct the model. So first model training will be there, followed by model testing will be there. Just wait for 2 minutes. Sir is joining.
Sorry for interruption. Extremely sorry. Here, hello. Am I audible or not, everybody?
Yes, sir. Yes, you are audible.
So here in this way, actually, the features are constructed if we follow vector space model, and the graph-based model is something else that's text processing. We're not going to talk about that. So after this feature construction here, what we have looking here. So the feature extraction, already we talked about the feature transformation can be divided into two ways. One is a feature construction, and another one is a feature extraction. Understand here in case of feature extraction, a new set of features are created from a combination of the original features. So we can have original features. From there, we are creating new features. Try to understand, we are not taking a subset of the feature. We are creating new set of features. So whenever we are creating new set of features, that is called feature extraction. So if we have Boolean features, this Boolean feature is not discussed, right? But just I'm telling here, if the features are Boolean, then to create the new features, we can use this kind of operations. The conjunction, disjunction, negations, and others can be used. Similarly, if you are having nominal features, then we can use a Cartesian product, M of n, and others operation can be done. And if we're having a numerical features, then for feature extraction, we can use mean, max, addition, subtraction, multiplication, division, average, equivalence, inequality, and others. Means different kind of operations can be done on the existing feature to extract new set of features. So here just to have a mathematical equation for that. See here, So now we are creating new features, and new features are represented by f bar. This f bar equals to function of f. These new features can be given here. From the new features, sorry, the original features can be given here as f. From the original features, we can create new set of features, that is f bar. So here the function is in expanded form. See here, we are creating a new feature, that is f1. And f1 is created from feature f1 and f2. This original f1 and f2. And this f1 is multiplied with the coefficients. It can be anything. You try to understand. This is an example only. Similarly, f2 is again multiplied with an coefficients. So after multiplying, it is added, and finally a new feature is created. In this way, the features are generally created. And whenever we do feature extraction, if the new set of feature is represented by m and the original set of feature is represented by small n, then the condition is m should be less than n, because we do feature extraction for compaction purpose to reduce the size of the features so that we are creating new set of features. Clear? So now we're coming here with an example. See here we have a set, and this is a feature set, and here we are having a 4 features: fit A, fit B, fit C, and fit D. Now our objective is to create only 2 features, and these are the functions we are going to use, right? So we are creating here fit 1, and fit 1 can be created how? It can be created by adding which one? Fit A and fit B. And fit A is multiplied with a coefficient that is 0.3, and fit B again multiplied with a coefficient that is 0.9. And finally, the final one is the value of the fit 1. Similarly here, fit 2, to create fit 2, we're using fit B, fit C, and fit D. And we are multiplying with some coefficient here, here, and also here, and finally added, and we create here fit 2. So see here, in that way, we can create all the values of all the observations. Because in the new observations, each observation is represented by only 2 values. And initially, each observation was represented by 4 values. So here see that we have 4 attributes, and after feature extraction, we're having only 2. So in that way, actually, feature extraction is done. And here we have an example of the feature extraction when I do kind of say this problem, image processing kind of problem. So this is the image, and here these are the features. These are the features for diabetic retinopathy. So this is, I'm not going to talk about that one, but here the features are extracted. What is that actually? Initially, see, this is the retina. In this retina, we're having number of features, means number of things, number of observable, or number of things, number of features are there. Number of things are there, right? So initially, what do we need to do? We need to do segmentation in case of image processing. After segmentation, and here we convert it into the gray level image. In the gray level image, we're looking that this kind of features are available. And now, whenever these are the small dots, these are represented by microaneurysm. These are called microaneurysm. And here we have a bit bigger dot. These are called hemorrhages. And a bigger dot, these are called exudates. In that way, different kind of features are there, and we have extracted all the features for predicting diabetic retinopathy, and these are the features. But you try to understand with the advent of deep learning, as a works of machine learning, that's what I'm talking about, those things, small things. With the advent of the deep learning, now this feature extraction especially for the image data is reduced. Especially the deep learning. Nowadays, people are using in different scenario, different situation. But a special thing of deep learning is that if we have a situation, and in that situation, if the feature space is not clear, in that situation, actually deep learning is used. That is the objective of deep learning. If the feature space is undefined, we don't know which kind of feature can be there. So in that case, actually, deep learning is used, especially if used for the categorical data. So it's a questionable whether you will get a better result or not, because different kind of operations are being done there. So it's a questionable. That's a big question in the deep learning community. So this is also an example of feature extraction. That example is given here. Now we're coming here, right? So there are different kind of feature extraction algorithms. Some of the popular feature extraction algorithm in machine learning, which we use generally, this is the set. These are the conventional and the popular feature extraction algorithm. Single value decomposition, linear discriminant analysis. Then we have principal component analysis, features linear discriminant. So now the mathematically we're going to discuss about with an example PCA, principal component analysis. Listen carefully. If you have any question, then you can put your question one by one. So now formally we are going to discuss about PCA. So going here. So why PCA is used? The first question, PCA is used if you're having, say, big dimensional data, or say multi-dimensional data, or we can say huge dimensional data. If you want to find a small pattern, or if you want to find a pattern from the high dimensions, then we need to use PCA. So principal component analysis can find a pattern from the high dimensional data, so that the high dimensional data can be represented by only few attributes or with only few dimensions. Especially this PCA is used for face recognition and image compression purpose. So main objective whenever we are having high dimensional data, to make it low dimensional without much loss of information, then that part can be done using PCA. So now we are going back into the mathematical formulation of PCA one by one. The first step of the PCA is what here, get some data. So initially we need to have data, only then we can do. And for your convenience and to understand very easily, here we have taken a data set where we have only two dimensions, x and y. So from this two dimension, our objective is to create only one dimension. Fine. So this is the initial data set, and these are the dimensions. We did not add here labels because in case of PCA, label is not required. From the set of input data, our objective is to reduce the size. That's the objective. So here we have, again repeating, here we have two dimensions, x and y. Our objective is to create only one dimension data so that size can be reduced, because this is an example. So whenever we have a big dimensional data, the same concept is used. So coming here in the step 2, in step 2 actually subtract the mean. By subtracting mean, it finds the data adjust. So step number 2 is to calculate the data adjust. Now the question, how to calculate the data adjust? See here. Initially, for each parameter, for each attribute, we have to find the mean value. So if you find the mean value of x, the mean is this. It's represented by x bar, that is 1.81. And now mean value of y, that is mean. You can't understand, mean means it's the average. So mean value of this one is how much? That is y bar, that is 1.91. So we found now mean of x and y. So if you have multiple attributes, then we need to find the multiple means. Okay, after finding the mean, now we have to find the data adjust. Name is what? Subtract the mean. So now for each process, what do we need to do? We need to subtract the mean from the original data. So here, if we talk about x, the original point is which one? 2.5. So now from 2.5, we have to subtract 1.81. So see here, from 2.5, we are subtracting 1.81. So it becomes how much? 0.69. And that's the value of the data adjust here. Similarly, for the y here, the value of y is how much? 2.4. So we have a 2.4 and subtracting here the mean, that is 1.91. So if you subtract this one, then it becomes 0.49. So this is the value here, 0.49 for against this value of y. Similarly, now we can calculate this subtracted mean for this value 0.5. Similarly, we can do a 2.2. Similarly, 1.9. In 1.9, what we need to do? 1.9 minus 1.81. So if you do this one, the value becomes 0.09. Similarly for 3.1. Similarly for 2.3. Similarly for all those for x's. Now similarly for all values of y, we need to do, and that value is stored here. So finally, this data is called data adjust. This part is clear, everybody? Any question here? Participant, any question here?
Any questions, participants? No, sir.
So after that, step number 2 is done. Now we're going to step number 3. And step number 3 is talking about now we need to calculate which one? We need to calculate covariance matrix of x and y, right? So here in this case, we're having a 2-dimensional. Fine. So whenever we're going to find a covariance matrix of some vectors, if it is 2, then the size of the covariance matrix would be 2 into 2. If it is 3, then it will be 3 into 3. So here we have 2 vectors. That's why the size of the covariance matrix is 2 into 2. And this covariance matrix finds the covariance of all the pairs. So if we have x and y, how many pairs we can calculate? So 4 pairs. The covariance of x comma x, covariance of x comma y, and here covariance y comma x, then covariance y comma y. So in that way, we have to design the covariance matrix now. Then we need to calculate the covariances. We're coming to that, right? So be clear here. In that way, we need to design the covariance matrix here. So now, if we calculate the covariance between one dimension and itself, one dimension means x and itself. In this case, the covariance is called variance, right? And the formula for the variance and covariance is given here. So if you find the variance, that is the covariance of x because we're having only single vector there. So here it is talking about summation of I to n. N is the total number of observations, how many observations we are having, right? Then xi, this is the observation, ith observation minus mean of x. And here again, ith observation and mixed mean of I. And finally, it is divided by in the total number of observation minus 1. So if you consider the value of n in our case, how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in our case, the value of n is 10. And the value of n minus 1 is 9. So similarly, we can do here. So here we have to find x, and here we have to find y, because now we're having 2 different vectors. And here we had 2 same vector. That's why we had this formula, because we're having this one and this one. To calculate cov x comma x and to calculate cov y comma y, we need to use this formula. And this is the formula of covariance. Try to understand, right? It's a simple mathematics. I'm telling you, if you are a student of machine learning, you need to know only 3 kinds of mathematics. That's sufficient, right? If you want to do the data science, that is the first one is probability, and then second one is statistics. And in statistics, you can have a different kind of thing, but you study only carefully descriptive statistics, then matrices or matrix algebra. If you are doing the data science, all the things will come under that. And if you are the people who are interested in doing research or doing work in the image processing, then you have to study Fourier transformation more, one more. So study those mathematics carefully. Everything is simple. You try to understand, things are very simple. So here we are standing here. That's it, covariance. This is the formula of covariance. It's a simple thing, right? So now we're going to calculate the covariances, because here we have seen the equations. Now to calculate the values here, so simply we can calculate here. How we can calculate? Because already this x minus x bar for all the observations already we have in the data adjust. You try to understand here. Well, but data adjust, that's why we have done this one. Data adjust. So from the data adjust, we'll get all those values. All those values. These values are available. What do we need to do? If we want to find which one here, cov. Initially, which one we're finding here? We are finding cov x comma y. Cov x comma y means which one? This formula, this equation. We're having cov x comma y, and here this is the formula. And you try to understand, all the values are available here, and here all the values of these are available here. So what we need to do for each observations, each observations, what do we need to do? We need to multiply this and this. For the first observation, the value of this one is this and this, so we need to multiply this and this. Simply you have multiplied here. See here, 0.69 into 0.49. This is the first observation. So in the value of n is how much? 10. So 10 times we need to do. So here again we're having the value minus 1.31. So minus 1.21. So similarly we multiplied here. You can see here the multiplied here. Plus the third one here, 0.39, 0.99. We have multiplied here 0.39 into 0.99. Similarly, we have multiplied all those things here, We have multiplied, right? Why? Because according to the equations, we need to find all the summation of all the data which are available in data, adjust data. So we found the upper part, the value of upper part is how much? That is 5.539. So see here, we have written here But to find curve x comma y, try to understand here, we are finding curve x comma y. So here the value is 5.539. By which one? By n minus 1. The value of n is 10. The 10 minus 1, that is what? How much? 9. So if we find the solution of this expression, then it becomes 0.6154. That's why we keep where this value where we keep this value here, because here we have curve x comma y, so we kept the value here. We kept the value here. Try to understand. We kept the value here. Done. The part is done. Now you try to understand this covariance. This one curve x comma y. This is equal to curve y comma x. We can change the sequence, but still the value is same. So that's why, as we have here, the same value is given here. Then two values we have calculated, this covariance and this covariance. Now we need to calculate this covariance. Already talked about which formula we need to have. This is the formula for that. This is the formula for that. So here what we need to do, each time the same thing, because this thing into this thing, xi minus x bar into xi minus x bar for all of the observations. And in our problem, we are having 10 observations. That's why 10 times we need to do this into this, this into this, this into this, this into this, like that. We have to do how many times? 10 times. And then it is divided by 9. So if we multiply 10 times x, the value become 5.549. And n minus 1, that is 9. So now to find the solution of this expression, it becomes 0.0165, like that. So here this value is kept here. Similarly, the same thing we need to do for which one? For y now. So if you multiply all those things, the value become how much? 6.4289. And it is divided by n minus 1, that is 9. So now find the solution of this expression. Now it becomes 0.6143 kind of thing. So it is given where? It is given here. So now we calculated the covariance matrix. Is it clear to everybody? Things are very simple. You try to understand. Just you need to keep track one by one. Any question?
Sir, one student wants you to repeat this once again.
Oh, repetition. Okay, fine. So see here, from here we are coming. Just I'll tell it very slowly and gradually here. So we need to have this kind of covariance matrix, right? Because we're having two attributes. That's why now the covariance matrix would be 2 into 2. If we have 3 attributes, then we need to calculate 3 into 3. So as we have x and y, that's why it is 2 into 2. So the covariance matrix is represented like that. Cov x comma x, cov this is like that. So whenever we have covariance x comma x, that is correctly the variance of x. And here, if the attributes are different, then that is the covariance. And now to find the covariances, these are the formula. These are the formula, the simple formula, right? The statistical formula, these are simple formula. So now we are coming here. And this is what? This already we know. Now we are interested to find the value of this one, covariance x comma y. We are interested to calculate this one, right? And the formula of this one is what? This is the formula. Here, see that I have written here the small x, but here I have written capital X, right? By mistake, it is boss. Try to understand, right? So here we have a small y, we have a capital Y here. And this is the formula. So you see carefully, these values, the values which are stored in the data adjust, these are what? X minus x bar, y minus y bar. And if you see here, the equation of the covariance, especially these expressions are there, xi minus x bar, yi minus y bar, these values are there. So from that adjust data, we'll get all the values. Fine. So it is talking about what? If we talk about the first observation, so it's talking about the multiplication of the first observation of this and first observation of this. So this is the first observation. Try to understand. This is the first observation. So now we need to multiply this and this. We have multiplied this and this here. Plus which one? Because this is summation plus the second observation. So this is the second observation. So in the second observation, what? This into this. So we written here this into this. Similarly, for third observation, we did this into this, the third observation. So how many observations we're having here? We're having 10 observations. So we have done here all those things for 10 observations, right? And finally, if we find the value, then it becomes 5.539. And in the equation, what? We have this one, and this one is divided by n minus 1. And the value of n in this problem is 10. That's why 10 minus 1, that is 9. So now if we keep this by 9, the value becomes this. This is the value, right? And this value is kept here where? Covariance of x comma y. Covariance of x comma y. And again, one thing should be remember here. The covariance of x comma y equals to covariance of y comma x. Fine. So that's why we have here this one. Similarly, we keep the value here. Done. And now we have to find the covariance of this. The formula to calculate the covariance of this is the variance of x, already talked about. And this is the equation for that. And here what we're doing, we are multiplying this with this. Means the same value. Means the subtraction of x into subtraction of x for each of the simple observations. So how many observations we're having? 10. For 10 times we have to do the same thing here. 0.69 into, for the first observation, when the value of n equals to 1. Or I equals to 1. Sorry, I equals to 1. Right? I can arrange 1 to n. N equals to 10. So when I equals to 1, so it represents first observation here, this one. So it's talking about what? It's talking about the subtraction from mean of which one? The first observation of x. So that is what? 0.69. This is 0.69 into again 0.69. Same thing is there. So now if you do, then how many times we need to do? We need to do 10 times here, right? Because summation of 1 to n. N is the 10. So that's why we have done here this into this first time plus this into this second time, this into this for the third observation, this into this for fourth observation, and finally we add it up. And if we add up finally, the value becomes 5.549 and it's divided by 9. And finally, if you find the value of this expression, it becomes 0.61 kind of thing. This is. So now this is kept where? This is kept here. Similarly, we have to do for the y. And we have done similarly all those things for y. And we got the value of the numerator, that is what? 6.4289. And the value of denominator is 9, that is n minus 1. So now if we found the value of x, that is 0.714 kind of thing. So this is now given here. So in that way, we have calculated the covariance matrix. Now I think it is clear, right? Don't repeat me so thrice. Fine. So now it is okay, I think.
Okay, sir.
So now it's okay. So we got the covariance matrix, right? Up to the covariance matrix. Now we are coming step number 4. And step number 4 is talking about calculate the eigenvectors and eigenvalues of covariance matrix. Many times in matrix calculation, or say matrix vector, you calculated eigenvalues and eigenvectors. And this is the one of the example of eigenvalues and eigenvectors where generally we use. That is Pca. So now from this covariance matrix, we need to find the eigenvalues and eigenvectors. So we found here the eigenvectors 1, eigenvector 2. These are represented like that, 1 and 2. Eigenvector 1, eigenvector 2. For eigenvector 1, the eigenvalues is this. For eigenvector 2, the eigenvalues is this. These eigenvalues are created from here. These eigenvalues are created from this matrix, right? This is out of this works of from your mathematics. When matrix calculation is there, you need to see carefully how to find eigenvalues and eigenvectors. So these are the eigenvalues and these are the eigenvectors. Fine. Now, some of the interesting things are here. Choosing components and forming a feature vector. Now we calculated eigenvalues and eigenvectors. Now we have to form the feature vector. How we can form the feature vector? There are certain concepts, and the concepts are here. So reading out the line, it turns out that the eigenvector with the highest eigenvalue is the principal component of the data. So what it's talking about is talking about the eigenvector for which the eigenvalue is the highest. That represents the principal component of the data. That's why the name is principal component analysis. So once we get the principal component, then what we can say? We can say most of the information of the data set we have in our hand, because now we got the principal component. Fine. So which one becomes the principal component? The eigenvectors with the highest eigenvalues. So out of these and these, this is the first eigenvalues for the first eigenvectors. This is the second. This is the eigenvalues for these eigenvectors. So out of these two eigenvectors here, we can see This eigenvalue, out of two eigenvalues, this eigenvalue is the highest. So now we can say this is the eigenvector, which is the principal component of the data set. Fine. So we now got the principal component. So it says the second line, see here, the eigenvector with the largest eigenvalues is the one that points the middle of the data. Wherever we get the eigenvectors with the highest eigenvalues, it's called principal component, and it points where it points. It points to the middle of the data. So middle of the data means what? The more this what? Maximum information about the data. Mean of the database we got here. This is that. And then which one? It is the most significant relationship between data dimension. This relationship is talking about this eigenvector and eigenvalue. So now we got, if our objective is now, so here it is clear, the eigenvector whose eigenvalue is the highest, that is the principal component. Fine. So we are coming to the, we are in this step, but now we're going to see the calculation to form which one? To form a feature vector. How to form a feature vector now? That's the concept. So now we got one thing. Feature vector means eigenvectors whose eigenvalues is highest. That is the principal component. Fine. So already we have this one. This is eigenvalues. This is eigenvectors. Now when we form the feature vectors are formed in that way. We can give your eigenvector 1, eigenvector 2, eigenvector 3, eigenvector 4 kind of things. These are according to the values of the eigenvalues. If the eigenvalues is the highest, this is the order of you can say decreasing or descending, not increasing. This is decreasing order of eigenvalues. So the first eigenvector is the eigenvector whose eigenvalues is the highest. Second eigenvector is the eigenvector whose eigenvalue is the second. Fine. But you try to understand, in this case, we are interested to find only one dimension. So that we need to calculate only one eigenvectors. So out of two eigenvectors, which one is the principal component whose eigenvalue is the highest? This one, because this, right? So that here, in place of 1, 2, 3, 4, just we're keeping only one, and that is this. So this is the principal component we got now, right? So we got the principal component, and we have a last step. Last step is talking about deriving the new data. Already talked about feature extraction means what? Feature extraction is going to extract the new set of features from the original one. So now we have to create, we got the principal component, right? That's the principal component. But if you try to understand, our database is represented by how many observations? 10 observations. So we need to have a 10 data, because each data is represented by one dimension. But if you try to understand total number of samples, we have 10. Right? So now what we do, we derive the new data set. How we can derive the new data set? See here, in this way we can derive the new data set. So we have to take the transpose of vector, means feature vector, and transpose of data adjust. Data, which one is data adjust? This is the data adjust. This is the data adjust, right? So now we have to take the transpose of this one and transpose of this one. So transpose of this one is this. So we have taken here only half 2 decimal point. Only we have taken here 2 decimal point, right? So that it becomes easier to show the multiplication. That I have taken the 2 decimal point here. 0.68 means which one? This one, right? 0.677. I have taken here 0.68, and here from 0.735 I have taken here 0.74, right? And this is the data adjust, and this is what? This is just transpose. And now what we can do? The rows can be multiplied with the columns. The columns can be multiplied by the rows actually in the multiplication. So we did the multiplication. That is the multiplication of the matrix. You have to know, right? So here what we can do, this one is multiplied with this one, plus this one is multiplied by this one. That one becomes the first value, right? That one becomes the first value of the matrix multiplication. So here what we have done, we multiply this into this, plus this into this. So if we solve this one, the value of this part would be 0.8318 minus 0.8318. Similarly, we have to calculate this into this. So if we calculate this into this, we'll get one value, and that is 1.782. Similarly, we have to calculate this into this. Then value becomes what? Minus 0.9978. Again, we have to do what? This into this. So if you multiply, then it becomes minus 0.2758. Similarly, this into this. So if you do this one, it becomes minus 1.6838. Like that, we have to do the multiplication, and finally we'll get the value. And this is the new value on the new data set from the original data set using Pca. Point is over, everybody. See here. Any question you can tell me.
Any questions, participants?
Very much tired. Okay, fine. No questions. So coming now next year. Question? No question. So coming here now. Feature extraction was completed. Feature construction, feature extraction we have completed. Now we are standing at feature selection. What is that actually? So feature selection is one the most critical in ML. In machine learning, feature selection is the most critical step. What does it do actually here? We actually find a subset of feature from the original set of feature, which gives all the significant information of the data set, by which we can reduce the size of the data. The feature selection does, or feature selection selects a subset of feature of the original features. It selects the subset of feature in such a way so that maximum information of the dataset can be conserved. So now you can have a question, what's the difference between feature selection and feature extraction? In case of feature extraction, we are creating new features. But in case of feature selection, what we're doing, we are keeping only a subset of features. We can have a 10 number of features. Out of 10, we can keep 7, 8. We are not creating any new feature in feature selection. Rather, we are keeping only a set of features. Fine. For example, here, see here that we have a data set here. We have a data set. So here the objective is to find the weight of a student. So now each student is described by roll number, age, height. Roll number, age, height, and this is the weight. Roll number, age, height, this is the weight. Roll number, age, height, this is the weight, right? So now we see carefully here. This weight cannot be related with the roll number. So in this scenario, roll number becomes a redundant data or irrelevant data for the problem, right? So if we have a such kind of data, then it has to be eliminated from the data set. So it is eliminated. Once we eliminated this one, then we'll have this data set. But one thing, you can have many questions now. So if we can do like that, then what is the use of feature selection? You try to understand. That's a so simple problem. As a small example, try to understand the iris data set. How many independent parameters we had? How many attributes? 4. And we have one class. Can you say which one is irrelevant? We cannot say. We cannot say. So we have to do certain kind of thing there. We have certain kind of measures there, so that we can understand which parameter is redundant, which parameter is irrelevant. So if you get irrelevant or redundant parameter, means attributes, then we have to remove those attributes from the data set. Here, I have shown you an example so that you can understand. See, if this kind of data is there, really, this data, this attribute really doesn't have any impact in finding the weight of a student because it's a roll number. So such kind of data can be in a data set. If we have a such kind of data in a data set, then how we can find? We can find using certain measures. We have all those measures. We're coming to discuss all those measures, right? Now, you can have a question. So why we do this kind of feature selection? If you don't do that, what's the problem? If we do the feature selection, especially, we can achieve two things. The first thing is that it can reduce the time complexity. As we are discarding one of the data from here, the size of the database becomes less because one of the activities is discarded from here. Because whenever we train or we make a model, the size of the data set is very huge, right? Million data, million data can be there in the real means a real classifier or in a real model. So if we discard one of them, it means what? We are discarding huge amount of data. So it enhances that, it reduces the time complexity, and also it reduces the space complexity. And whenever the data is reduced, somehow the complexity of the classifier becomes less. Means whenever we design a classifier, we need to do a lot of computation, right? So whenever less number of data is there, then the complexity of the algorithm becomes less. This is one of the reasons. Another reason is that whenever we do feature selection, sometimes the accuracy of the classifier improves. you may have a question here. So if we discarded whether accuracy may be improved, yes, it may be improved. Why? Because if you are familiar with nonlinear problem, many times some spatial or some missions attribute make a data set or make a problem nonlinear. If you can find that missions attribute and if you can say discard that one from there, then somehow this nonlinear problem can be a bit linear. So whenever the problem becomes a bit linear, then automatically the accuracy improves. Fine. So now, should we do feature selection or not? Yes, we do, because we are earning here. We are obtaining two things: the time complexity and the accuracy. But why should we should do? Whether our data set is very big? Yes, our data set is very big, because nowadays we are handling with different kind of multi-dimensional data, or you can say high-dimensional data. For an example, DNA analysis, the GIS system, and then social networking. Social networking is what? Text analysis from say Twitter, text analysis from Facebook, from different shopping sites, right? Online shopping site. So you can have a million and million data. And whenever the observation is represented, for an example, in say movie review, we have seen that I have shown you only 8 different features are there. But you try to understand, if practically, if you see, there can be thousands and thousands of different keywords there. So if you're having different thousands and thousands keywords, then it becomes high dimensional database. So if you're having high dimensional database, then somehow this high dimensional database has to be reduced. Then we need to have a feature selection, right? And there is one term in some machine learning that is called picking effect. What is that actually? It is believed that if we are having sufficient large database, if we increase the number of features, then generally, as long as the database size is increasing, or as long as the database size is large, then the performance generally increases if we increase the attributes or the features. But I try to understand, if you're having a small database and if we increase the feature, then the performance drops. That case is that scenario is called picking effect, right? So if we have a small database, if we increase the number of features, then automatically the performance drops, and that event is called picking effect. So if we do feature selection, then this phenomena, the chances of this phenomena will reduce somehow, because there won't be a picking effect, because we are reducing which one? The features from the data set. So for this reason, actually the feature selection we do or has to be done. Now the question, when you do feature selection, what do actually we do internally? But you know only the feature selection term, and these are the algorithms, right? But internally, what does it do actually? When you do feature selection, it does two things. Those things are feature relevance. It finds the feature relevance, and also it finds the feature redundancy. What is the feature relevance? Relevance means whether the feature is significant or not. Based on the feature relevance, the features can be classified into three categories. One is called irrelevant feature, weakly relevant feature, and the relevant feature. So if we have some irrelevant feature, it means what? It doesn't contribute anything in the classification or to solve the problem. For an example, here in this case, this roll number is irrelevant feature, because roll number doesn't have any impact in finding the weight of a student, right? So then again, we can have a weakly relevant feature. The features which are weakly relevant means significant but less significant. Fine. So if we have such kind of feature, if we say reduce those feature, then automatically the performance will degrade. And a type of feature that is a relevant feature, the features are very much informative, and it has huge impact in classification or solving the problem. So that kind of feature is called a relevant feature. A relevant feature is called significant feature. So in feature selection, the one thing what we do that is called feature relevance. We find the feature relevance, whether the feature is relevant or not. If we find that feature is not irrelevant, then we discard it. Now the question, how we can do feature relevance? To do feature relevance, we're having a number of matrices. We're going to see all those matrices, fine? So another thing that the feature selection does, that is called feature redundancy. What is that actually? Try to understand carefully here. So here we're going to talk about the feature redundancy. Here you see, after discarding this roll number, we're having what? We're having age and height. So using this age and height, our objective is to find the weights. So looking here, the age is 12 and height is how much? 1.1. The weight is how much? That is 23. Now the weight is decreased by some measure, that is 21.6, right? 21.6. As the weight is decreasing, we are looking the trend of age and height. We are looking age is also decreasing, right? And height is also decreasing. Both are decreasing. If this one is decreasing, both are decreasing. Now this one is increasing, 24/7. Looking, the height is increasing because here the height was 1.05 and here it is 1.2. And here age is also increasing. There is 13 now. Looking here, the weight is now decreasing, 21.3. Looking, it is 1.03. It is also decreasing. 13 to 11, it is also decreasing. So we are looking that whenever weight is increasing, both are increasing. Weight is decreasing, then both are decreasing. So now if you find the linear relationship between age and height, we are looking that the linear relationship is same. If it is increasing, it is also increasing. If it is decreasing, it is also decreasing for each of the observations. If so, then it is believed in machine learning. If we keep one of them, still the information of the data set can be conserved. So in such a case, if this phenomena happens, then we can say feature age and feature height, they are redundant. As they are redundant, then one of them should be deleted from here. Now you have a question, sir. So both are redundant, age and height. Then which one should be deleted? It's a big question now. So how we can delete? Then we can find the relevance of age separately to solve this problem, and also we can find the relevance level of height separately to solve this problem. Then we'll keep the features whose relevance is higher, and we'll delete the feature whose relevance, or we remove the feature whose relevance is less. In that way you can do. This is one of the way. You can have a different way also for deleting one of the redundant attributes or the features. Clear? So now here the summary is that in feature selection, generally two things are done, and these are the feature selection and feature redundancy. Now coming here, so by how we can find the feature relevance, we can find feature relevance using mutual information and information gain. There are a number of parameters, there are a number of measures, but these measures are very popular measures. This information gain is very popular, right? So here we have all those discussion about the information gain, but I'm not going to talk about, because the decision tree is generally based on this information gain. So when we talk about the decision tree, I'll discuss. So I'm not going to discuss here because we don't have sufficient time to discuss all those things. So I'm skipping, but still in decision tree, this thing is required to find the significant features. So that's why I'm skipping this part here. So after that, that feature relevance has gone here. So now the feature redundancy. So how we can find two features are redundant? In that problem, we have the size of the small database was very small, and we analyzed and we found that one of them can be redundant. Now, whenever we have a big database, how we can say we cannot analyze by our empty eyes? We cannot do. So for that one, we are having different kind of measures. For that, we are having two kinds of measures. One is called similarity-based measures. Another one is called distance-based measure. In similarity-based measure, we are having this kind of measures by which we can find the similarity. If they are very much similar, then we can say they are redundant. If they are not similar, then we can say they are not redundant. And here we have some of the similarity measure, and these are Pearson correlation coefficients, one of them. A Spearman correlation, Kendall's tau, Jaccard index. Then we have simple matching coefficients, cosine similarity. This cosine similarity is very much popular in case of text analysis or text mining, cosine similarity. And then we have a distance measure, the Euclidean distance, Manhattan distance. Already we talk about, right? By these two distance, we can find whether the features are similar or not. But as a distance-based similarity, but you try to understand whenever we have certain kind of linear dependency between two variables, between two vectors, or between two features, then using distance-based similarity we cannot find. So in such a case, we need to have correlation-based similarity. So if you find the correlation-based similarity, then you can find whether certain kind of linear dependency is there or not. Sometimes maybe get to you linear dependency, very simple term, but I did not make any graph for that. So now we're coming here, one of them. The first one is what? The first one is called Pearson correlation coefficient. What is that actually? It finds the linear dependency between two vectors or two variables. Linear dependency. If linear dependency is high, then we can say they are similar. That linear dependency is calculated by a factor, by a coefficient, alpha. This alpha is nothing. This alpha is what? Covariance between f and 1, because here f1 and f2, because here objective is to find the similarity between. If they are very much similar, then we can say they are redundant, right? So our objective is to find the similarity. So that similarity is found using, calculated here using the Pearson correlation coefficient. So that is alpha here. Alpha equals to covariance f1, f2, means covariance of feature 1 and feature 2. Already we have seen that how to calculate covariance, right? So we can have two vectors. Simply we can calculate the covariance by root over of variance of f1 into variance of f2. So already we know all those formula, right? Because we have done Pca. So we can calculate this covariance variance from the two vectors or the two variables. Then finally we'll get a score, right? And this score actually ranges in between +1 and -1. +1 means two features are exactly similar. Two features are exactly similar. If the score is -1, then we can say two features are exactly dissimilar. There is no similarity between two. But you try to understand when you design, or when you want to do feature selection kind of thing, then we have to define a threshold value. If it crosses that threshold, then we can say they are the similar. So for an example here, we can give the value that is 0.6 or 0.7. So whenever it becomes 0.7 and above, means this score, this alpha, then we can say feature F1 and feature F2, they are very much similar. So they are redundant. So one of them has to be removed from here. So we can apply any of the criteria already we have discussed about, right? So this is called Pearson correlation coefficients. Now we are having the next one that is called a Spearman's correlation coefficient, right? There's another correlation coefficient. It measures what? Same thing. It measures linear dependency between two variables. But you try to understand here, this method, this mechanism, or this technique is not going to use the value of the vector. Rather, it uses the rank of the vectors. So here in this case, data is represented like that. If it is x is represented by x to the power r. X to the power is nothing. This is rank of x. So see here, one of the vector is here, right? One of the vector. This is one of the vector, right? This x. How this x can be represented? Now this x is represented in case of Spearman's correlations using the ranks. So how we can find the ranks? Now say for the smaller the rank is 1. So the smallest one is which one? -5. That's why the rank of -5 is 1. Rank of 0 is how much? 2. Rank of 3 is how much? Sorry, rank of 4 is how much? 3. Rank of 7 is how much? That is 4. Like that, for each of the vector, we are finding the ranks. These are the ranks. These are the ranks. Clear? So now these ranks, this is the rank of the one vector. Similarly, we can have y here. So again, we can find the ranks here. Now we can use those ranks here in the covariance to calculate covariance and variance of f1 and variance of f2. And finally, we can find a score that is Spearman's correlation coefficient. Again, these Spearman correlation coefficients can range in between +1 and -1. +1 means they are exactly same. -1 means they are completely different, right? And again, here we can give a threshold value. Threshold can be 0.6 or 0.7. If it crosses the threshold, then we can say they are very much similar. So one of them should be deleted from there. And see here, one statement given here: if S greater than, means Spearman correlation coefficient greater than Pearson correlation coefficient, it means that we have a monotonic relationship, not a linear relationship, right? So to find whether linear relationship is there or not, what we can do, we can find S and P, then we can compare whether S greater than P or not. If it is, then we can say there is no linear relationship. After that, we have a Kindle stove here. Using Kindle stove, we have a problem. We can solve the problem very easily. So with an example, I can show you. Just give me 1 to 2 minutes break. I'm very much exhausted really. 1 minute or 2 minute break taking. Then we'll discuss this. So here we're talking about the Kendall's tau. This is another measure for finding the correlations between two variables or two vectors. It also measures the linear dependency between two vectors. It also uses the ranks. The Kendall's tau works very well for a bigger size of data. It works very well. But the time complexity of Kendall's tau is a bit better than the Spearman correlation. But it works better than the Spearman correlation, according to the characteristic of the algorithm, right? So again, in this case, if data are x and y, data can be represented by x to the power r. Means data are represented by their ranks. Similarly, here also, it can calculate a value in between +1 and -1. Fine. So now we're coming here, the equation of the Kendall's tau. Kendall's tau, we're having different kind of versions. So here we're talking about the first version of the Kendall's tau, so that you can understand how it works. Actually. So here we have this is called concordant and this is called discordant. So here our objective is to find the concordant and the discordant. So concordant minus discordant by this concordant plus discordant. Using this formula, we can solve the problem. Next, we'll do code part, right? So all feature selection, Pca kind of thing we'll do. We'll apply Pca, then we'll find the performance and all kind of things, whichever we have done and whichever part is left in, say, imbalance data, we'll do all those things next day. Today, we are going to solve this problem here. So how the Kendall's tau solve the problem, whether two features are similar or not. That's our objective here. So now already we talk about each of the feature is represented by the ranks. So this is the rank of the first feature, and this is the rank of the second feature. So we have given the ranks of both the features here, right? It means the feature values. We have given the ranks here. Make a table of rankings. The rankings of the feature 1 should be in ascending order. So here the ranking of the feature 1 has to be ranked in ascending order. So already here in this case we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 kind of things, so that we can put all those things here. And the corresponding pairs should be given here, right? So for an example, if they are not in ascending order already, if they are not in order, then what we need to do, see here carefully. So looking here, the first items, the first value is the rank is first, second value's rank is second, third value's rank is third, fourth value's rank is fourth, but fifth value's rank is 12, and 12th value's rank is fifth. Then what we need to do? We need to swap, because our objective is to arrange feature 1 in ascending order. So now we are swapping, we are keeping this 5 here. Keeping this 5 means here means 1. At the same time, the corresponding rank of feature 2 has to be replaced, because here we're going to find a linear relationship of the values. So if we put 5 here, then 11 should be kept here. Similarly, whenever the 12 is kept here, 6 would be here, in that way actually, fine? So whichever ranks we can have, but the ranks has to be arranged in ascending order. Which rank? The rank of the first feature. So already in this problem, the rank of the first feature is already arranged in ascending order. And their corresponding values are given one by one here, right? Values are given here. So now we are finding the first step is what? Count the number of concordant pairs using the second columns. Now the question, what is the concordant pairs? Concordant pairs are how many larger ranks are below a certain rank. For an example, we want to calculate the concordant pairs of 1. So we have to see how many items are there, or how many ranks are there below this one whose rank is higher than 1. That is called concordant. That's why it says that concordant pairs are how many larger ranks are below a certain rank. So how many larger below 1? So below 1 we have a 2. So this is larger, 1. 4 is again larger than 1. So 2. 3 is again larger than 1. This is 3, 4, 5, 6, 7, 8, 9, 10, 11. That's why the concordant of 1 is 11. So this 11 has to be written here. Similarly, we have to find the concordant for all the values, all the ranks of feature 2. So for 2, how many ranks are below? Greater than 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All are greater. That's why the concordant of this one is 10 here. Now see 4. So how many values are there, larger values below 4. So 3 is not larger, so it's not counted now. 6 is larger than 4, yes, 1. 5 is larger than 4, yes, 2, 3, 4, 5, 6, 7, 8. So that's why the concordant of 4 is 8 here. The concordant is 3 of 3 is how much? 8. Similarly, you can count here, how many big rank means higher ranks are below 3. If you count, it becomes 8. 1, 2, 3, 4, 5, 6, 7, 8. Similarly, from 6, how many? This is not 1, 2, 3, 4, 5, 6. That's why it's 6. From 5, how many? 1, 2, 3, 4, 5, 6. That's why 6. Similarly for 8, similarly for 7, similarly for 10, similarly for 9, and similarly for 12. But for 11, we cannot count because below 11, there is no rank. That's why we cannot find any concordant for 11 here. So we found the concordant of the pairs of the feature 2. Now we are coming here to find the discordant. Count the number of discordant pairs and insert them in the next column here. Discordant pair of which one? Discordant pair of feature 2, ranks of feature 2. So what is discordant? How we can calculate? The number of discordant pair is similar to step 2. Only we are looking for smaller ranks. In case of concordant, we are looking how many higher ranks below a particular rank. But in this case, we are looking how many a smaller rank below a particular rank. So if you talk about 1, none of the rank is below 1. None of the rank is lower than 1. So below we have a number of ranks, but none of them is lower than 1. That's why the discordant of this 1 becomes how much? 0. Discordant of 2 become how much? 0, because none of them is lower than 2. Similarly, now see 4. How many lower than 4? Only 1, 3. Rank 3 is lower than 4. That's why the value is 1 here. Now calculate here how many lower than 3, below, none of them. That's why this is 0. How many lower than that? Only 1. That's why 1. Similarly, we calculated all those things up to 12. So these are the discordant values, concordant values, and these are the discordant values. So now we got up to step number 3. Now we are looking for the step number 4. Step number 4 is talking what? It's talking sum the values in column Y. So column wise, find the sum. So here, if you find the sum of the concordant, then it becomes 61. Sum of the discordant, how much? That is 5 only. Now insert the total into the formula. So total, we got the totals, and we know the total is here, right? These are the totals, and we know the Kendall-Stau formula. Kendall-Stau is talking about what? C minus D by C plus D. So see, the value of C is how much? That's 61. We kept here 61 minus D. Value of D is how much? That is 5. So we kept here 5 by C plus D. 61 plus 5. So if you solve this expression, then finally we'll get the value that is 0.85. So now find the correlation between F1 and F2 using Kendall-Stau. Then we're finding that the correlation becomes 0.8.5. So the Tau's coefficient is 0.85, suggesting a strong relationship between the rankings or between the features. So between the features, there is a strong relationship because here the coefficient becomes 0.85. As I said, strong correlationship, it means what? They are very much similar. So our score can be what? Threshold. Say, for an example, threshold is 0.7. So it crosses the threshold. So now this pair become redundant pair, F1 and F2. Right? It's a redundant pair. That's why we need to delete one of them. We can delete one of them from here. So how we can delete? We can find the relevance of this one and relevance of this one. This is one of the way. You can have a different way also. The feature whose relevance level is less, then that one can be discarded. Right? So in that way, actually find the correlation score between two vectors to find the redundancy. The feature selection actually does two things. It finds the relevance of the feature and it finds the feature redundancy. And then it does, right? Then it does. If we find the calculation, if we find, say statistical computation, then those things says like that. But we can have the wrapper method, filter. We are going to talk about all those things. Then you can see these are the statistical method now we're talking about. So after that, here we have a perfect if say this is the case. Now if they are exactly similar, to cross check whether it finds 1 or not. Now see, they are exactly similar, right? The rank of F1, this same, and rank of F2 exactly similar. 1 1, 2 2, 3 3, 4 4, 5 5, 6 6, 7 7, 8 8, 9 9, 10 10, 11 11, like that. Now similarly we can calculate the concordant here. So if you find the concordant becomes like that. These are the concordant. Already we just discussed the description of the concordant. And for the discordant, for all cases, becomes 0 0 0 0 0, because they are already in ascending order. So 0 0 0 0. Summation becomes how much? 66. This is 0. Now if you keep these values here in the candle's tau, then we can look that the value becomes 1. So whenever we have exact values, whenever the linear behavior of the two variables is same, then exactly we'll get exact 1. So if we have exactly 1, it means what? The variables are exactly similar, right? So you try to understand the values of this feature and values of this feature can be different. Can be different. This one can be different. But if we arrange in ascending order, then the ranks of all those values of feature 2 would be like that, same as the ranks of the feature value 1. If they are same, if we make a graph like that, if feature 1 goes like that, then feature 2 will go like that, or like that, exactly parallel kind of thing, or you can say linear kind of thing. So it means what? Even if we find the distance similarity, that it cannot be 0. There can be huge distance between two features, but you try to understand their behavior is same. That is called linear behavior. As the linear behavior is same, that's why we are finding the correlation between feature 1 and feature 2, that is 1. So using Kendall's tau measure or correlation coefficient. So in this way, actually, we calculate. So after that, this one cosine similarity, today not going to discuss, I think. Yeah, fine, the cosine similarity, say that we complete this cosine similarity. Next, we do only say this one, lab, or practical we do. So here, this cosine similarity, what it does, what it finds actually, the cosine similarity calculates the cosine angle between two vectors, right? If the cosine similarity can take on values between -1 and plus, the score we can get +1 and -1 in between that, right? If the vector points in the exact same direction, then the cosine similarity becomes +1. If in case of cosine similarity, find the direction of two vectors. If the direction of two vectors in the same direction, exactly same direction, then it finds the value +1. +1 means the vectors are very much similar, right? If the vectors point in opposite direction, then the cosine similarity scores -1, means their directions are exactly opposite, means they are exactly dissimilar. So if they are exactly dissimilar, then we can find a value that is -1. So the range of cosine similarity also range between -1 and +1. +1 means they're exactly similar. -1 means they are not similar at all. They are exactly opposite. And now to calculate the cosine similarity, we have this formula. See, x comma y, we're finding with x is a vector, y is another vector. X dot y divided by norm of x. This is called norm, vector calculation, right? In the matrix calculation. So norm of x and norm of y. So now if we expand the formula, then formula becomes like that here. So here we're finding what? And the pairwise multiplication we are finding between x and y. And here what? Root over the square of x and root over square of y for all the values. Simply, right? Simply all for all the values. So now if we have the x1 vector, which is represented by 2 4 0 0 2 1 3 0 0, and if we have another vector y, and that is represented by 2 1 0 0 3 2 1 0 1, then the cosine similarity now we're going to calculate here. So initially this part we have to calculate the numerator. This is x dot y. Simply we can multiply 2 into 2. So 2 into 2 plus 4 into 1. So 4 into 1 plus 0 into 0, third into third. 4 into 4, 0 into 0. Similarly, we can calculate all those things, and finally we can get a value on the numerator, and that is 19. Here we have a 19, right? Similarly, now we need to calculate which one? This one, right? This, the norm of x. This norm of x, this formula. So this formula root over, this is the first value whole square So first value, which one? 2. That's why 2 is square plus 4 is square plus 0 is square, like that. If we find the norm of x, this is the formula. Simply we have all the values of the vector. We can keep here, and now we can get value of the norm of x, that is 5.83. Similarly, we can find the norm of y here, and the values are here available, right? So we can keep all the values here, here, like that. So we can calculate 4.47. So now we keep all those values here in this equation, cosine similarity. So numerator 19, so 19 by this into this. So finally, it will find 0.729. So cosine similarity is between x and y. If the values are like that, then it's 0.729. So now if we have a threshold value that is, say, 0.7, then we can say x1 and x and y, they are similar because their cosine similarity crosses the threshold, which was given 0.7. That's why they are similar. So this pair is a redundant pair. Then one of them should be deleted from here. Okay, so this is cosine similarity. We'll not discuss all those things. We'll not discuss this. Next day, we'll discuss about the feature selection approaches and feature selection techniques. And before that, we'll do hands-on, because we have done feature extraction, feature construction, and some part is left in imbalanced data set. We'll do all those kind of practicals, and then we'll be discussing about the feature selection. So to your information, after feature selection, we're having a different kind of feature selection method. After that, we'll have which one? Model selection here. So different kind of models we can have, a supervised, unsupervised, and different kind of algorithms will come. Then how to do the training, especially we do hold out method. And hold out method is having some kind of problem. To overcome that one, we have to do cross validation. But again, in cross validation, there can be certain kind of drawback. Then we have to do bootstrapping. Those kind of methods are there. Then we have to do evaluation. Then you can use different kind of machine learning algorithms to solve different kind of problems. Because you on an average, whenever this evaluation part is over, so all kinds of issues which can arise to design one model. Okay, thank you. Do you have any question?
Any questions, participants?
Question? No question. Fine. Okay. Thank you, madam.
Thank you so much, sir. Thank you for your valuable session, sir. We'll meet again tomorrow. Thank you so much.